So the first important definition that we looked at already a little bit is stationary points. That's whenever your tangent is equal to 0. So whenever your slope is 0, what that would look like is you might have a maximum, you might have a minimum, and we're also going to see that sometimes you could have a point like this. So as far as describing those three, we call them three types. There's the relative maximum points, the relative minimum points, and that one in between that I graphed, that's called a stationary point of inflection. Stationary points to start off with. So this one here would be a maximum, a relative maximum, this one a relative minimum, and this one we're going to call a stationary point of inflection. So those are the three times that when you take the derivative and make it equal to 0, that's one of three possibilities that could happen. Now, in order to tell which kind they are, we'll get to our first and second derivative test. Just some more definitions. We call things relative maximums or relative minimums if they're only a maximum or minimum over a small area, and they're called an absolute or global maximum or minimum if that's the biggest point it ever gets. So like on a parabola, if a parabola opens up, that would be an absolute minimum because the graph never gets lower than that. But on an x cubed graph, this is a relative maximum because it's a maximum in that small area, but later on the graph does get bigger than that. And this would be a relative minimum because it's a minimum in this small area, but the graph does get smaller at another area. And there's our inflection point. Now, you're going to learn later on an inflection point is where a graph changes something called concavity. And concavity is how the graph is bending. So for example, this part here, the graph is bent like that, and we would call that concave down. And afterwards, this part, the graph is bent upwards like that, and we'd call that concave up. In a graph, there's certain points where the graph changes from being concave down to concave up. Think about an x cubed graph. It's a great example. Some places it's concave up, and some places it's concave down. There's a point somewhere in between where it changes from being concave down to concave up. That's called an inflection point. Sometimes those inflection points happen to also have a tangent which is equal to 0. So can you see at that blue point that this is concave down and this part over here is concave up? And at that point it changed. And if that point also has a derivative of 0, that's why we call it a stationary point of inflection. So some terminology there. So we were doing this last class a bit already. We just didn't give it a name. The first derivative test is to find out and to be able to classify what those stationary points are. Are they relative maximums? Are they relative minimums? Or are they stationary points of inflection? So what we're going to do is we're going to find out where they're equal to 0, and then find out by making that sign diagram whether our graph changes from increasing to decreasing or from decreasing to increasing. So for our relative maximum, what's going to happen? You're going to find out our critical point where the derivative is equal to 0. So just as an example, let's say if we had this, our derivative would be 2x minus 2, and if we set that equal to 0, you would find out that x is equal to 1. So your critical point would be 1. Your first derivative test would say, well, what happens to our derivative before 1? If you plugged in something less than 1 into your derivative, you would find out that you get a negative number. So if you plugged in negative 3, you get a negative number. What that means is our function has slopes that are negative. Anytime your slopes are negative, it means that your original graph would have to be decreasing. And anything above 1, if you plug that into the derivative, you'd find out it's positive, so that would say that it's increasing. And that would tell you that at the point 1, you have a minimum, because if your graph is going down from left to right and then going up, that would tell you that that has to be a minimum. Similarly, if you went the other way and you saw something go up and then go down after, you would have a maximum. So we're going to look for our critical numbers. We're going to figure out what happens before and after them in those intervals, and then you can tell if it's a maximum or a minimum. So you get a maximum point whenever you change from an increasing function to a decreasing function. And it'll become quite visible from our graph that that's what's going to happen. And you have a minimum whenever you're changing from a decreasing function to an increasing function. So here's our first example. We're going to find the stationary point in this one, and we're going to show that it's a maximum using that first derivative test. So to start off with, we need to find out where those tangents are equal to 0, where we can find our critical points. So we take our derivative, negative 2x plus 5, set it equal to 0. And we find out that our tangent is equal to 0 when x is equal to 5 over 2, or 2.5. Our first derivative test, then, is where we set up our number line and we put our critical point on that number line. And we check values before and after that critical point. And we plug those values into our derivative because we want to find out if the slopes are positive or negative before and after 5 over 2. So choose a number before 5 over 2, like negative 10. Here, you're going to see that you're going to get positive 20 plus 5. You don't need to know the exact value. You just have to find out, our numbers in that section, are they going to be positive or negative? And since they're positive, all the slopes are positive means that your function is increasing. If you try something bigger than 5 over 2, say 10, plug that in, negative 20 plus 5, this is going to be negative in this section, so it's going to be going down. Now, you probably already knew this just looking at the equation. Looking at the equation, we have a negative x squared graph. You know that that's a parabola, and you know that that's a parabola opening down. So you already should have this vision in your head, and the first derivative test should just verify what you already know. What did we find out by taking the derivative? We found out that this point, our vertex, happens when x is 5 over 2. We don't know the y-coordinate of that. We could find that out if we wanted to by plugging it into the original equation and figuring out what we would get. So if I wanted to find that y-coordinate, I could plug it into my original equation. Negative 5 over 2 squared plus 5 times 5 over 2 minus 7. And I'd figure out exactly where that vertex is. Yes? Because if I'm trying to find the point on my graph, the graph is my original equation. If I plug in 5 over 2 into my derivative tells me the slopes of tangents. So when I plug in 5 over 2 into the derivative, it's going to tell me that the slope of the tangent there is equal to 0 because it's perfectly flat. Yes, come on in. So again, so when we plug in 5 over 2 into our derivative, that'll always tell us the slope of a tangent line. So when I plug 5 over 2 into our derivative, I get 0 because I know that at that maximum point, my slope's going to be 0. When I plug in 5 over 2 into my function, that's going to tell me my actual point. So if I were to do that, negative plus I get negative 3/4 or negative 0.75. So that tells me where my vertex is, where my maximum is going to be at. The 5 over 2 is where m is equal to 0. And that's important because I want to find that maximum point. On a parabola, that's a key point. On any graph, our maximums or our minimums are key points that are going to help us graph it. So because in my first derivative test, I show that my function is increasing from left to right, then decreasing, I now know that this is a max, a local maximum. In this case, it's actually an absolute maximum because it's a parabola. Now, you already knew it was a maximum because you knew something about parabolas, and if the coefficient of x squared is negative, your parabola is opening down. But now we've shown it using the first derivative test. So how could we write a statement to represent this? Since f of x is increasing before x equals 5 over 2, and we know that because f prime of x is greater than 0 before x equals 5 over 2. And decreasing after x equals 5 over 2. And of course, we know that because f prime of x is less than 0 after x equals 5 over 2. Yeah, I know. Here I have to write a little bit. That's why it's so messy. So, since f of x is increasing before x equals 5 over 2, decreasing after x equals 5 over 2, we have a maximum at this point. That would be how you could write it, showing that you know the first derivative test. So the first derivative test is showing that if a function is changing from increasing to decreasing at a point, it has to be a maximum. And that's what happened in our case. Our function was increasing before, decreasing after, so we know it's a maximum. So here, we're going to want to show that it's a minimum. We're going to have to write a statement to say that it's decreasing before and increasing after. So again, find your derivative. Find out where your derivative is equal to 0. You should have got x equals 2. When you plug 2 back into your original equation to find the actual point, you're going to get negative 3. So 2 comma negative 3 is the point on your graph that's going to be your vertex. And then when you do your first derivative test, before 2, when you plug that into your derivative, you're going to get a negative value. After 2, you're going to get a positive value. And then your statement, since f prime of x is less than 0 before x equals 2, meaning that your function is decreasing, and f prime of x is bigger than 0 after x equals 2, which means your function is increasing, we know that 2 comma negative 3 is a local minimum. Now, many of you have graphing calculators. You know how to graph a function into your graphing calculator. Once you put it into y equals, there is things in your calculator to find maxes and mins. And that can be very helpful just to check if you're doing things correctly. So what we're going to do here is we're going to just quickly type in the function that we just had there, which was 2x squared minus 8x plus 5. There's going to be a part that's calculator and a part that's not. So there we have that parabola. If I wanted to find out where that minimum was, which we found already, what we could do is we can go second, calculate, number 3, the minimum. It's going to ask you to go to the left side and the right side. You can either do that by clicking your arrows back and forth. My cursor currently is to the left side, so I can push enter. My calculator draws a nice little line, so I can see for sure I am to the left of that minimum. Then I need to go to the right side. I can either keep clicking until I get to the right side, or you can type a value. For example, if I can see right away that 5 is to the right of it, and I push enter, it'll put a line at 5. Then when I calculate and guess, it finds out 2.00000004, y equals negative 3. Okay? The calculator is actually wrong because we figured it out exactly to be 2 comma negative 3. So a little bit of explanation. And did yours come out to even different numbers? Yeah. So both of our answers, if we rounded them, would round to 2. A little bit of understanding of what the calculator is doing. The calculator is using a process of thousands of calculations and getting closer and closer and closer to the answer. So it checks between 2 answers, and then whichever one's the minimum, it takes that answer. Then it checks between 2 others, and it slowly narrows in on this value. Now, because at a certain point the calculator feels it got close enough, it stops and produces the answer. So it's not actually doing calculus like we did to figure it out. It's doing a process of a million calculations to figure it out. So where at this point in your career you can say, I am smarter than my calculator, because you're able to find this more accurate. But it's sometimes nice to be able to have that calculus. You've done the calculus, you want to check your answer to see if you were in the right, had the right idea. The graphing calculator can be very helpful for that. So now we're going to look at those stationary points of inflection. Again, to draw a little picture, that happens like in an x cubed graph, where you have a point where the tangent is equal to 0, but it's not a maximum or a minimum. So we still have the slope of our tangent equal to 0. But when we do our sign diagram for this, so if this was x cubed, you can see that you would know that that point is at 0, 0. When you do your first derivative, you'd get 3x squared, and if you try to make that equal to 0, what would x have to be? Well, x would have to be 0. So when we draw our sign diagram and we put our critical point of 0 here, what happens when you try a number less than 0 into 3x squared? Well, it's going to be positive, meaning that our function is going up. What happens when you try a positive number into 3x squared? It's also positive, meaning that it's going to go up, which we can see in our graph. It's increasing and then keeps increasing. Even though it levels out, at that point. If this is the case, then you don't have a maximum or a minimum, and you'd have a stationary point of inflection. So either it has to keep increasing like we saw in this graph, or keep decreasing, and then you would have one of these points, a bend in your graph. You remember bends in your graph with your multiplicity from last year when you graph something like that, right? So what did this graph look like? Well, you knew you had an x-intercept at 3, and you knew you had an x-intercept at 2. And this is an x to the 5 graph, positive x to the 5 graph, which acts very much like a line with a positive slope. So your graph is going to be starting down here. When it hit 2, it bounced off, and when it hit here, it bent. Well, my bend is at a bad spot, but that was the idea. And this is what this graph looks like. What you would find with calculus is you would find the slope is 0 here, you'd find the slope is 0 there, and you'd find the slope is 0 there. And we're going to find out that if we get a stationary point of inflection, like we did in this last example here, if you were to take the second derivative, so for 3x squared, that's the first derivative. If I were to take the second derivative, I would get 6x. And you would find that the second derivative is also equal to 0 at that same point. And we're going to find this out later when we graph more things, that our second derivative is going to find all of our inflection points, not just these stationary points of inflection. All right, so now we're going to have a bunch of examples to look at, and we're going to sketch the graphs of each of them. Y equals x cubed plus 3x squared plus 1. So if we take our first derivative, we'll get 3x squared plus 6x. If we want to find all our stationary points, we're going to set this equal to 0. If we factor this, we find out that our derivative is equal to 0 at x equals 0 and x equals negative 2. So now if we go to our first derivative test and draw our line, our number line, put negative 2 on there and put 0 on there, and find out what's happening to our graph at these different points. And again, when figuring out where it's positive and negative, it often is easiest to use the factored form of the line. So if you were to try something less than negative 2, like negative 5, this first thing is going to be negative. 3 times negative 5 is going to be negative 15. Then you're going to multiply by our second factor, and if I plug in negative 5 into there, that's also negative. A negative times a negative is positive, so I know this section is positive, and our original graph is increasing. If I try between negative 2 and 0, like negative 1, 3 times negative 1 will still be negative, but negative 1 plus 2 will be positive. And so negative times a positive is negative, and now we know that this function is decreasing. So at negative 2, we already know we have a maximum on our graph. If we try something larger than 0, 3 times 5 or 3 times 10 is positive. 5 plus 2 is still positive. Positive times positive is positive again. So this is what our first derivative test is telling us. It's going from increasing to decreasing to increasing. So now we can say some things about these points. Negative 2 comma something is going to be a local max. And 0 comma something is a local minimum. What are those points going to be, though? How am I going to find the y-coordinate of those points? I'm trying to find a point on my graph, so I have to go back to my original equation and plug that in. Can you see that if I plug in negative 2, I'm going to get negative 8 plus 12 is 4 plus 1 is 5. So negative 2 comma 5. And if I plug in 0, I'm going to get 0 comma 1. So now to sketch our graph, what do we know? We know we have 0 comma 1. And we know we have negative 2 comma positive 5. And since our graph is increasing till we hit that maximum, then decreasing till we hit that minimum, and then increasing afterwards, this is what we have for our graph. Some stuff you remember from last year in grade 12. This was an x cubed graph. X cubed graphs, if we scroll up to the original graph here, x cubed graphs that are positive look like this. You don't know how many bends there are or what they exactly look like, but you knew that general shape from last year. The only thing that we solved for last year was where our x-intercepts and y-intercepts were. And we could find our x-intercepts if we could factor, and we could find our y-intercepts by plugging in 0 for x. Unfortunately, this one doesn't factor nicely. So there's no way to nicely find this x-intercept right here other than with a graphing calculator. We could have found this y-intercept, but from last year you wouldn't have known that it was a local minimum. You would just know that your graph went through that point. You also wouldn't have known how high your graph goes. So now the calculus is telling us where that maximum is, where the minimum is, when it's increasing, when it's decreasing, so we can draw a much more accurate graph than we could from last year. Just different notation for function. Same idea. Here we have a function, so if we took the derivative, set it equal to 0, you could factor out a 4x squared. And you'd find that x equals 0 and x equals 3 are critical points. Again, to find out your first derivative test, there we go, I'm writing less words. Doing a good job of being a mathematician. Again, if we're going to find out where it's increasing or where it's decreasing, we're always plugging that into our derivative function. Again, I'm going to use the factored form, so if I plug in something less than 0, can you see that 4x squared, whether it's less than 0 or bigger than 0, anywhere is always going to be positive because it's x squared. So really, I'm only worried about the x minus 3. And when x is less than 0, it's going to be negative. So this first section is going to be negative, meaning our function is decreasing. Between 0 and 3, what are we going to find? If you plug in 2, this is still, x minus 3 is still going to be negative. it's still going to be decreasing. And after 3, now this factor is going to be positive. So now this is increasing. So what does that tell us? 0 comma something is a stationary point of inflection. And 3 comma something is a local min. What are the actual points? Well, then we'd have to plug back into our original equation. So when you plug in 0, you're going to get 0 comma 0. When you plug in 3, we're going to get 81 minus 27 times 4, which is 108, negative 27. So now we got those values. What does that mean for our graph? We've got 0 comma 0 and 3 comma negative 27. It's decreasing, hits this point but stays decreasing, so you have a bend, goes through that point perfectly, and then back up again. Draw our arrowheads on both ends of the graph. So this is what calculus is telling us this graph looks like. Again, I'm going to review what you learned from last year when you graphed this same function in grade 12. What you would have done last year for this function is you would have just been able to find x-intercepts and y-intercepts. And because it's an x to the 4 graph and it's positive, you knew it acted like a positive parabola. Even functions act like parabolas. So if it's an x to the 4, x to the 6, x to the 8, and it's positive, it acts like a parabola that opens up. If it's negative, it would act like a parabola opening down. All of your odd functions acted like lines. Positive odd functions had a positive slope, went from the bottom up to the top. Negative odd functions acted like negative lines. Yes? We're going to find that out. We're going to find that out using what we would have learned from last year. So last year, you would have found out your y-intercept by plugging in 0. And so on your grid paper, you would have already known you had 0, 0. In order to find your x-intercepts, you would have factored. And this one actually factors nicely. You can factor out an x cubed, leaving you with x minus 4. So it would have told you that 0, 0 was also an x-intercept, which you already knew, but you would have 4 comma 0 as your other point. So that tells us a little bit more about our graph. By factoring, we could have found this other x-intercept to be 4 comma 0. Since this has a multiplicity of 3, you would have learned that there was a bend in your graph. And so your graph would have come down, bent here but gone through, and then gone through 4 as well, because its multiplicity was 1. Anytime a multiplicity had 1, your graph went through it. Anytime it had an odd multiplicity that was bigger than 1, like 3 or 5, you had a bend in your graph. And anytime that you had an even multiplicity, that's when your graph hit the x-axis and bounced off of it. Now with calculus, what we're able to see is we're able to see that there's the bend because it's a stationary point of inflection. You still need the slope at that point to be 0, so that's why that bend has to be there. We also were able to find how far down this went. Last year when you graphed, you didn't have to worry about how far it went. You just knew that it would have to go through that point again. And so by factoring the original function, we can find our x-intercept to make our graph clear. So that's something we're always going to do. We're always going to find our x-intercepts and y-intercepts as much as we can by factoring and by plugging in x equals 0. But now we can find these maximums and minimums, these stationary points, and be able to classify them as either local minimums or local maximums.